you doing? Seb here from Circuits and Sounds. I welcome you to the third part of episode 1, the Phat Philter.
She's fat. PH, fat.
I'm thinking today we'll take a dedicated look at our MS-20 style filter, which is one of the most popular DIY designs out there, and for good reason, because this thing sounds incredible. But before we start getting into some patches with it, let's first find out what a filter actually is. So for that, let's ask old mate here. Filter. Any electronic or acoustic device that blocks signals at certain frequencies while allowing others to pass. So that's exactly how this works. It allows certain frequencies to pass through to other modules while blocking other ones entirely. In this case, it's considered a low-pass filter, so lower frequency signals can pass through, but higher frequency signals are blocked entirely. So to explain this a bit further, I think it's diagram time. So today's lovely drawing is a graph of our low-pass filter frequency response, with our gain on the y-axis in dB, and our frequency along the x-axis in hertz. And as you can see, this whole thing isn't to scale at all. So if we follow our curve, we can see that we have this slope on a downwards trend towards minus 30 dB as the frequency increases. So we can see that the higher frequencies in the signal are attenuated further and further, whereas the low frequencies in the signal sit happily here at 0 dB. And this point here, where our signal dips down to minus 3 dB, is known as our cutoff frequency, denoted by this formula just here, where R represents the resistor value and C represents the capacitor value, which we'll get to just in a minute. A low-pass filter isn't the only kind of filter that we can actually use. There are also other ones known as a high-pass or even a band-pass. In a high-pass filter, it basically works in the opposite direction. So our lower frequency signals are attenuated, and our higher frequency signals sit happily at 0 dB. And a band-pass filter is a combination of a low-pass and a high-pass. So we essentially get two different cutoffs where we can move the band in and out. But since our filter is just a low-pass filter, we'll just focus on how that one works today. So a low-pass filter is essentially just a resistor and a very wonky capacitor. So a low-pass filter is essentially just a resistor and a capacitor. So we take our input from this side and our output from this side, and this is where the formula comes into play. We can determine our cutoff frequency depending on the value of the resistor and the capacitor. And a high-pass filter is basically just the opposite. We move the capacitor over here and the resistor down here. So to put all this talk into practice, let's build this on a breadboard and we'll see how it works. And then we can start and build up a picture of how the MS-20 filter works. So I've made our little low-pass filter on the breadboard just here, with some music on the iPad, copyright free of course, which is going into our buffered multiple, which essentially creates 3 copies of the same signal. So we take one copy and put it into the mixer so that we can hear the original signal, and then we take another copy to put through the filter, and then also put that through the mixer. So then we can hear the difference between the original signal and the filtered signal. I'm using some music to demonstrate the filter, as music has lots of different frequencies that all kind of mash together. So the effect of the cutoff is a lot more pronounced than just using the oscillator. I first have the signal going into a 0.1 UF capacitor to block any DC elements. It then goes through a 100k resistor and then through a 0.001 UF capacitor, which is connected to virtual ground, made up of this resistor divider just here. So if we put these values into our formula, then we can see that our cutoff is around 1600 Hz, which is close to the cutoff for 2000 Hz like we had in our graph. I chose this value as it seemed like a bit of a Goldilocks number, not too low, but not too high, just enough to demonstrate how we can filter out certain frequencies within music. So if I unmute the original signal, we start to get an idea of what it sounds like. But let's unmute the filtered version. And you can hear how those higher frequencies are being cut out. So let's compare them again. You can hear it particularly more in the drums of the song. Alright, so this is kind of fun, but it's not really that exciting. But what we can do is replace this resistor down here with a potentiometer, so that we can actually shift the cutoff frequency to where we want it. So let's do that and see what it sounds like. So I've got our potentiometer wired in, so now that we can actually adjust the cutoff frequency. So let's listen to the original again. Now the filtered one. So let's adjust our potentiometer. And you can hear how the higher frequencies are filtered out as we increase the cutoff. Now let's see what happens when we actually swap the capacitor and the potentiometer, just to quickly demonstrate what a high pass filter sounds like. So let's unmute our signal again. Now you can hear how the low frequencies are being cut out. Now another thing you'll notice is that there was quite a large difference in volume between the original signal and the filtered signal. This is because it's a passive filter. There's no power involved in it at all, apart from this little virtual ground, but that doesn't really count. So this is where we bring in an op-amp to maintain the signal gain between the two versions. So we've now replaced our passive low-pass filter with an active low-pass filter just by using an op-amp. So if I unmute the filtered signal, we can hear how we can adjust the cutoff frequency. But let's compare this to the original signal. I don't hear much of a volume drop at all, and this is the beauty of an active filter. But using a simple one like this, it acts more like a volume control. And the thing that makes a filter really cool is resonance. So let's go back to the whiteboard and explain how that works. So what is resonance? If we look at this point here where a frequency begins to cut off, if we actually have the cutoff point sort of rise up a little bit so that it actually goes above 0 dB and causes the filter to self-oscillate. And this is usually achieved by feeding some of the output signal back into the input signal. So to demonstrate a filter with resonance, this is where the MS-20 filter finally comes in. So let's take a quick look at what we have here. We have our input with a drive control where we can crank the signal a little bit, which is a feature that I added to the original circuit. The cutoff, where we can adjust the cutoff frequency, which also has 3 CV controls over it. 2 with dedicated level controls, and 1 direct volt per octave input, where we can technically plug in a keyboard and play the filter when we crank the resonance, which leads me to the resonance control, where we can adjust how close to self-oscillation, or even fully into self-oscillation, we can push the filter. Another feature that I've added is this Vectoral-based resonance control, where we can modulate how far we push the filter into self-oscillation, which also has a level control. And then finally, the output. You will also notice that there was this random hole just here. That's because I'm planning to add a high pass input, so we can use the filter to cut off the low frequencies. But that's a project for another day. So without further ado, Let's finally start to hear what this thing actually sounds like. So I have one of our oscillators from the TTO going into the filter, and then out into the mixer for recording. But if I now move the cutoff, we can start to hear the tone from the oscillator starting to come through. Now I'll leave that where it is, just to quickly demonstrate this drive, which basically just cranks the volume a little bit. It actually seems to mess with the oscillator a little bit as well. We'll leave it just there to give it a bit of a boost. Now you can hear that the filter was acting much like the simple ones that we made before, in that the cutoff is basically working like a volume control. But what happens if we turn up the resonance to just near self-oscillation? We start to get these really spacey, squelchy sounds out of it. And this is the beauty of resonance, because it adds so much character to a filter. So while we're talking about resonance, I think we should demonstrate the resonance control voltage. So for that, we don't even need the input signal. We can just pull that straight out. And I'll turn this down a little bit, just because the resonance is very loud. So I move the cutoff to just about there. So now we have pushed the filter fully into self-oscillation. So it's basically creating a sine wave, and we can adjust the frequency with the cutoff. And this is how we're able to play the filter, like I was talking about before with the volt per octave input. If we have the resonance cranked right up, then we can almost play this like a sort of another oscillator. But I'll leave that there, and I'll take the LFO through a patch cable and stick it into the Res CV. Turn up the level. And now you can hear how the resonance is being modulated by the rate of the LFO. We can adjust its level. So let's replace it with the envelope generator. Sounds like a police siren now. Alright, you get the idea. So now that we've demonstrated the resonance control voltage, let's have a look at the control voltage inputs for the cutoff. So I'll move that up a bit. And I'll take our LFO and stick it into the CV2. Speed it up a bit. Change that to a different waveform. And we can adjust its level of modulation. Now let's see what happens when we replace it with the envelope generator. Now let's see what happens when we connect both modulation sources in. You just get all kinds of madness now. Alright, that's enough of that. So now let's see what happens when we apply modulation to the volt per octave input, where we have no level control and apply the full modulation as it is. So we'll move the cutoff a little bit. We'll take our LFO. Now I'll replace it with the envelope generator. And as you can imagine, it's a bit annoying not having a level control for the volt per octave input. And that's because it's not really designed for this kind of modulation. What it is better suited to is audio rate or frequency modulation. So let's see what happens when we take another oscillator from the TTO and put that into the volt per octave input. So I now have another oscillator connected into the volt per octave input. So if I unmute the signal, move the cutoff, we get these kind of resonant vocal vowel sounds. Almost like the sounds of a dying monk in a lot of distress. But we can play around with the modulating frequency and the oscillator that is also going into the filter. And we get these sounds almost reminiscent of tuning a radio of sorts. As well as some almost digital sounding sounds. Almost like sort of bit crushed alias sort of sounding things. But I just want to show you what happens when I connect the envelope generator. Over into our individual CV. It almost sounds like an engine from a Star Wars movie starting up and then going into this kind of resonant vocal vowel sort of sound. It's bizarre, it's crazy, but I love it. Alright, that's enough of that. So now that we have heard some of the sounds that this thing can make, I think it's time to have a look at the circuit behind the panel, which is based on the Korg MS-20 Filter clone by Rene Schmitz. So a few things to note before we start getting into it. The original circuit was designed for positive and minus 15 volts, but I've scaled it to my 0 to 12 volt standard, and it still seems to work just fine. So just remember that any ground connection you see goes to virtual ground, and any negative connection goes to actual ground. So up here, we can see a voltage summer, where we have our CV and volt per octave inputs and the cutoff control. Also note that all of these controls are fed directly into the base of this transistor here, rather than using an op-amp for the summing. Our CV inputs are connected directly to the top of these 47k linear potentiometers, which I've changed to 50k in my design just to keep it simpler. So we can adjust the level of modulation applied to the cutoff. The volt per octave or pitch input, we can see has no level control at all. It's just simply a current limiting resistor connected to the input, and our cutoff control is just a pot wire between -15 and +15, or 0 to 12 volt in our case, to apply the full range of voltage to our old friend just here. The LV tech, which like in the TTO, is used to convert the linear voltage changes into an exponential current. This is also another reason why we can play the filter through the volt per octave input, due to our perceptions with frequency. As we have covered this part in the TTO, we don't need to go into the details again, but we should just note that these transistors here are PNP type, unlike the TTO LV tech, which uses NPN transistors. This is because it is designed to work as a current source, rather than a current sink. So next we come to the actual filter itself, which is two identical Salem key type filters. You can see that we have a few op amps floating about, but what exactly are these funny looking ones here with these Venn diagram looking things on the output? Well, these are known as operational transconductance amplifiers, or OTAs for short, which essentially work as a voltage-controlled current source. They are actually found at the heart of heaps of analog synth circuits just because of how useful they are. In our case, these CA3080s have been replaced with LM13700s, but they basically work the same as each other. So how exactly do these OTAs work? Well, let me quickly pull up the symbol for one, and we can take a look at each pin. We have our inverting and non-inverting inputs, which function exactly like an op amp does. However, the differential voltage going into these pins must be kept between 10 to 20 millivolt for low distortion operation, / not blowing the chip up. In the middle here, we have this pin known as the diode bias, which can be used to improve the linearity and distortion when using a bit of a higher voltage into the inputs. Generally though, it isn't really needed if the voltage is kept between 10 to 20 millivolt. At the top and the bottom here, we can see our power pins, which can be used with both single rail and dual rail power supplies. On the right hand side, we have our output, which creates a current based on the differential voltage applied to the inputs multiplied by the transconductance, which is controlled by this pin just here, which is what sets the relationship between the input and output currents of the OTA. The current flowing into this pin, which should be no more than 2 mA, controls how much current flows from the output. OTA chips like the LM13700 also have onboard transistor buffers, just to help improve the distortion again, but they aren't actually used in this design. If you want some more details about OTAs, there are heaps of great resources just on the first page of Google, as well as the data sheet, which has an absolute shit ton of data, parameters and example circuits. 37 pages in fact. I know because I printed out the whole damn thing. But moving back to our filter circuit, which I'm not going to go into the absolute details about, because I'll be honest, I don't totally understand it myself. But the LV tech basically controls how much current is on the output of the OTAs, and therefore where the cutoff frequency lies. Again, details on how OTA filters work can be found in the data sheet, which gives an absolute wealth of information, more than I could surmise in a few short sentences. We also see these op-amp buffers here on the output of each filter stage. These are basically just being used to replace the onboard transistor buffers, as op-amps offer much higher input impedances and therefore less unwanted interaction with any previous circuit stages. And then finally, we can see this op-amp down here being used to feed some of the output back into the input, which is how we achieve our resonance. Also with a level control just here. We have a few LEDs, which were originally just diodes in the actual Korg filter, in the op-amp's feedback path as well, which gives some fun lights to look at when playing with the filter. We should also have a look at the couple of modifications I made to the original circuit. Here on the input, I replaced the original resistor with a 50k potentiometer, so we can adjust the gain and give the input signal a bit of a boost. To be honest, I didn't know if I was better off turning this resistor here into a potentiometer, or this resistor here into a potentiometer, but it seemed to crank the signal a bit, which is all I wanted, so if it ain't broke, don't fix it, as they say. Over on the resonance control, we also see this funny looking arrangement, which is the Vactrol based control voltage input. So what exactly is a Vactrol? In its simplest form, it is basically just an LED and LDR next to each other, wrapped up tight in some heat shrink. This gives the action of creating what is known as a voltage controlled resistor. There were lots of different ways to make a VCR, but this method is simple and also gives a bit of propagation delay, or slewing, between the components. which gives it a more natural feeling, akin to acoustic musical instruments. But we basically plug a CV source into the input, which goes through this current limiting resistor and lights up the LED, which in turn changes the resistance of the LDR. This is then wired in parallel with the resonance control, so that they can both affect the resonance together. There was also a level control for the Vactrol, which I've forgotten to draw, but it is wired in the exact same way as the CV controls. The top of the pot just connects to our jack, and the middle pin goes to the current limiting resistor. I think I might leave this episode where it's at for today. Join me next time where we'll start and take a look at the VCA, where we can modulate the volume of a tone coming from the oscillator. We'll also take a look at the envelope extractor, where we can put in an AC signal and turn it into a CV source for any of the other modules. See you next time!